All right, so the next part, and I should have went to the next slide. Sorry about that. Let me erase this stuff as well. So the next key concept is that sodium, potassium, calcium, and phosphate levels are tightly regulated. So we're going to talk about each one of those specifically. And so first, we're going to talk about overview of salts or electrolytes. So salts are a type of electrolyte that dissociate in solution, but salts do not give off the hydrogen ions, so they're not acids. These are salts. So we have dietary intake of salts through food, fluids, and there is some metabolic salts that get released. Like when we break down bone with our osteoclast, that's going to release some metabolic salts as well. So let me see where I'm at in our lecture notes. Yeah, okay, we're good there. So, and I guess I'll write that down because it's not in your lecture notes, but that dietary intake is going to be food, not food, fluids, and some metabolic from the breakdown of bone via osteoclasts. So that's how we intake salt. How we get rid of salt is through our sweat. Now, sweat is usually hypotonic, but more sweat or water loss means more salt loss. So even though sweat is hypotonic, it doesn't have a whole lot of salt in it, but the more you sweat, the more salt you are going to lose. Feces. There are certain GI disorders can lead to excessive salt loss as well. And then we'll also lose salt through our urine and our vomit as well. So there is both input and output of salts in our body. So next is Addison's disease, which I think we may have brought up in endocrine, but this is when we have a lack of aldosterone. When we have a lack of aldosterone, then we're not reabsorbing that sodium into the blood, and that sodium is going to leave through our urine. And then if we have more sodium in our urine, water is going to follow, and so we'll have a higher urine output due to that loss of sodium. And so because you're lacking that salt in your blood, because you're losing it through your urine, because you're lacking aldosterone, and therefore not getting that reabsorption of salt or sodium through that sodium potassium pump, then you also have some salty food cravings as a result. Many people who are lacking aldosterone, because the adrenal cortex also produces cortisol, they may also be lacking some cortisol as well. And so what they may feel, some symptoms they may be experiencing include extreme fatigue, weight loss, because they're not holding on to much water, decreased blood pressure, so they're not reabsorbing the sodium or the water, so their blood volume and therefore blood pressure may decrease. And so they may actually experience some fainting because of that loss of blood pressure, and as well as depression. Lack of sodium can also lead to depression. Okay. The next disorder is pica, and I'm going to erase these because an image is going to come up right now. But pica is a lack of minerals. Usually iron is usually the culprit for pica. But you crave abnormal substances with this disorder. And that includes things like chalk, clay, burnt match tips, could also be like dried paint. But you're craving these really abnormal substances because you're lacking a very important mineral. And again, a lot of times it's going to be iron. And so the treatment for this is, one, treat the complications of you eating the chalk or the clay or the dried paint or the burnt match tips. You treat those complications as well as treating the imbalance. Make sure that we get more of that mineral that you're lacking, as well as treat any complications that you may have from eating those non-food items. All right, so like we said, about 90% of the solute in the extracellular fluid is sodium. We need that sodium outside the cell for that depolarization and for many other different things as well. So we said that each fluid compartment has a total concentration of 300 milliosmoles. 280 of those 300 actually comes from sodium. And so we already talked about the effects of hyponatremia. Now we're going to talk about the effects of hypernatremia. And so I'll talk about the differences in concentration between the two, but hypernatremia is when you have greater than 145. Remember that outside the cell, we should have about 140 milliequivalents per liter for sodium. So if we go above 145, that's considered hypernatremia. If we go less than 135 milliequivalents per liter, that is considered hyponatremia, which we already talked about. And so with hypernatremia, which we'll focus on here, it's usually due to, and I'll make this box a little bit bigger, due to inadequate take. So if you're not taking in enough water, then your cells are going to be more concentrated, and your blood plasma is also going to be more concentrated than it should, and therefore leading to hypernatremia. So due to inadequate water intake, or could be fluid loss. So if you lose fluid loss, that's going to cause an increase in concentration in your blood and extracellular fluid. And then in very rare cases, it could be due to an increase, and it's like a dramatic increase in sodium intake. And this is more rare to happen, but it can. If somebody intakes something that's very, very salty and lots of it, it can also lead to hypernatremia. And so symptoms or signs that they're going to be experiencing is going to be fatigue, excessive thirst, because there's too concentrated. We already talked about that thirst mechanism. Remember, excessive thirst, that term is polydipsia. Also experience muscle twitches, because again, any imbalance in sodium is going to mess with action potentials and membrane potentials, and so you may get some muscle twitches as well as seizures as well. You may experience seizures. Treatment for this would be water intake, increased water intake, or also IV fluids. Now, people who have problems with hypernatremia, too much salt, they can take like a salt substitute. So they can take like potassium chloride instead for their food to season their food. However, if someone is going to switch to a salt substitute like potassium chloride, they need to make sure that they have good aldosterone function, because remember, aldosterone is going to cause reabsorption of sodium and then secretion or cause us to get rid of any excess potassium. And so if you're taking potassium chloride as your seasoning, as a salt substitute, and I'll write it right here, calcium chloride can be a salt substitute. If we're taking an extra potassium, but our aldosterone isn't functioning correctly, then we're not going to be able to secrete enough potassium to keep up, because remember, our blood levels of potassium should only be about 4 milliequivalents per liter. And so if we are taking in extra potassium, but our aldosterone is not working to secrete that extra potassium, then we can end up with hyperkalemia, which we'll talk about a little bit later. So you can take a salt substitute if you have sodium problems or blood pressure problems, but you always have to make sure that your aldosterone is working correctly. Okay, I'm gonna erase these notes here, and I think that's it. And just a note, anytime you have an imbalance of sodium, because water and sodium are so closely tied, you're gonna have an issue with water balance as well. All right, so if you have a decrease in sodium content, that's going to cause that RAA pathway as well. It's going to trigger renin release and increase angiotensin 2, which is going to cause the adrenal cortex to release more aldosterone. It's going to tell the kidney tubules to turn on that sodium potassium pump so that we reabsorb more sodium and we can bring our sodium levels back to normal. But remember, anytime we trigger the work of aldosterone. It uses a sodium potassium pump. So every time we reabsorb sodium, we're also secreting or getting rid of potassium. So this is the same mechanism that works if we take in too much potassium. So if you are using a salt substitute and you have an increase in potassium coming in, then you can trigger this pathway and cause aldosterone to get rid of that excess potassium as well. Okay. And then make sure that you remember these cells that are detecting levels of sodium in the filtrate in our urinary system are part of that juxtaglomerular complex. And they are called macula densa cells. So make sure you remember that as well. And then remember that pathway is part of an even larger pathway of maintaining blood pressure homeostasis. This is that whole RA pathway, but kind of broken up into smaller sections. Okay, going back to endocrine, make sure that you remember ANP. ANP is going to be an antagonist to aldosterone, so it's going to inhibit that sodium reabsorption and prevent sodium retention. So if we have too high of a blood pressure, because remember ANP stands for atrial natriuretic peptide, it is the one, it's going to be triggered when you have too high blood pressure, because remember the RA pathway is when you have too low of blood pressure, so that you can reabsorb more sodium, reabsorb more water, and bring that blood pressure back up. ANP is going to work when your blood pressure is too high, so it's going to work in the opposite direction. And so if we have stretch of atria of the heart due to high blood pressure, that's going to release or cause the release of ANP, which is going to cause the granular cells of the kidneys to lessen the renin release, less angiotensin II, so less of that whole RA pathway. And it's actually going to cause the vessels to dilate to bring down that blood pressure. It's also going to cause less of ADH release and less of aldosterone release, so that we have less reabsorption of sodium and water. And therefore our blood volume can decrease if we're not reabsorbing as much, and therefore decrease our blood pressure. So this is going to work in opposition to that RAA pathway. So a lot of this is just review. Influence of other hormones. So I wonder if this is already in your lecture notes. Yes, it is. So estrogen is chemically similar to aldosterone, and this image here should be familiar from the female reproductive system lecture, but estrogen is very chemically similar to aldosterone. And so it increases both water and sodium retention, which is why right in the middle of your cycle, you do experience some bloating right before and around ovulation. But then progesterone actually has the opposite effect. And so when we have higher levels of progesterone towards the end of our cycles, and I'm saying ours, talking about women, but at the end of a woman's cycle, when progesterone levels are higher, it actually has an opposite effect. You tend to lose water, lose that bloat towards the end of the cycle. Okay. And I'm talking about a 30-day cycle here. Cushing's disease, we already know about this. This is usually caused by an overprescription of glucocorticoids or steroids, but it can also be caused by, and let me make sure what's in your lecture notes. Okay, it doesn't say. But we said before that Cushing's disease is usually caused by an overprescription of glucocorticoids. So I'll just write all that here. So it's when we have an increase in steroids or cortisol, and this can be an overprescription, or it could be if you have like a chronic disorder like asthma or rheumatoid arthritis that causes a release of cortisol very often, because it's a stressful disorder and causes lots of issues chronically all the time. Also can be caused by a tumor, either a tumor of your adrenal glands, because it's your adrenal cortex that releases that cortisol, or a tumor on your pituitary gland, which your anterior pituitary gland releases adrenocorticotropic hormone, which we didn't talk a whole lot about, but it's going to cause the release of more cortisol from the adrenal gland. So both of these things can cause, and an overprescription of glucocorticoids can cause this Cushing syndrome, which, remember, release of cortisol causes mobilization of fat, so it makes it so that more fat is available in case you're in a very stressful, like life or death situation, don't know when your next meal is going to be. It makes more energy available in your blood, but if that energy or that fat's not being used, it gets deposited in other spaces like that fat pad or the buffalo hump that you would get on the back of your neck. Also, not only is it going to cause that, but it also enhances reabsorption of sodium, so you get more water retention, and so you may get bloating in the abdomen as well. So that's Cushing's disease. But that's also review. So regulation of potassium, this is the most important intracellular cation. So most important intracellular cation. While the sodium is the most important extracellular cation. We have lots of sodium on the outside of the cell, but lots of potassium inside the cell. So this is the most important intracellular cation. And this is all in your lecture notes, and we've said it a million times before. You have a low concentration of potassium outside the cell in the ECF, about 4 milliequivalents per liter, but a very high concentration of potassium inside the cell at about 140 milliequivalents per liter, which is necessary for membrane potential and excitable cells. So we can have the correct setup to have repolarization and the efflux of potassium at the later half of the action potential. We talked about this during heart physiology, that both hyper and hypokalemia can cause fatal arrhythmias because, again, potassium is so important for the repolarization of cells and membrane potential. So it can cause fatal arrhythmias and be really, really hard on your heart. And because we secrete it mostly, so potassium is mostly secreted due to those sodium potassium pumps that we just talked about. And so having dietary intake of potassium is super important because we're constantly getting rid of so much all day. So dietary intake is important. And this is in your notes as well. And so meats, dairies, fruits, vegetables, grains should all have potassium in it. So just make sure you're getting enough potassium because, again, we're just getting rid of so much on a daily basis that we need to make sure that we're constantly intaking that potassium. And then remember that if you have problem with blood pressure and you're taking a salt substitute to combat that, you want to make sure you have healthy aldosterone function so that you're not experiencing hyperkalemia, which again can be hard on the heart. And then dialysis patients, because they're having kidney issues where maybe that sodium potassium pump is not doing its job the way it should, the aldosterone is not being utilized the way that it should. Many people who are on dialysis do experience hyperkalemia or too much potassium in their blood in between their dialysis sessions because those sodium potassium pumps aren't working the way that they should. Okay. So yeah, potassium, we need to make sure that we get it in our diet because we have a very limited ability to retain it because those sodium potassium pumps in our urinary system cause us to secrete so much of it. So this next diagram is to show how acidosis leads to hyperkalemia. So if you have acidosis, so acidosis is low pH, also high amounts of hydrogen ions. So if we have, in this little box here is representing our plasma. So if we have too much hydrogen ions in our blood, so we're acidotic, we're experiencing acidosis, those extra hydrogen ions are actually going to make their way inside of our red blood cells. So because we just have excess of them, they are going to eventually go into our red blood cells, and I'll make it a darker color. Sorry about that. They're going to make their way into our cells. And so we've learned this so much before with like the chloride shift and the alkaline tide and things like that, that we want to make sure that we maintain our memory potential. So if we gain a positive, we need to lose a positive. And so because we're bringing in this excess hydrogen ions into our red blood cells because there's too much of it, the positive ion that we have the most of inside our cells that we just talked about, 140 milliequivalents per liter, we have a potassium. That is the easiest one to exchange for that hydrogen ion. So again, we're experiencing acidosis, too much hydrogen ions in our blood. So we move that excess of hydrogen ions into our red blood cells. And the positive ion that our red blood cells have the most of, that it can more easily exchange with that hydrogen ion, is potassium. So we have so much potassium that a positive hydrogen comes in, and so then a positive potassium goes out, displacing more of that potassium in our blood. And in our blood, we should only have a level of 4 milliequivalents per liter of that potassium. So if we're shifting all this potassium into our blood, that is going to lead to hyperkalemia, which can lead to some fatal arrhythmias. So acidosis can lead to and is often associated with hyperkalemia. Okay. All right, regulation of calcium, you should already know about this. This is nothing new. Learned in Bio 32. So parathyroid hormone is the hormone that we count on for calcium homeostasis. So we have too low blood calcium, which is called hypocalcemia. This is going to stimulate the parathyroid glands to release parathyroid hormone. The three targets for parathyroid hormone are the bone, specifically the osteoclasts. We trigger the osteoclast to break down bone material so that we can release extra calcium back into the blood. That's one way to release calcium levels in the blood. We're also, the PTH is also going to target the kidneys so that we reabsorb more calcium in our kidney tubules. So that also will increase blood levels of calcium. And then lastly, PTH is going to promote the activation of vitamin D, which is going to cause more calcium absorption from our food. So more of the calcium that we eat is going to be placed into our blood, which is the third way that we're going to increase blood calcium levels. So I think in your notes, it asks you the three areas targeted. That's going to be the osteoclasts, the kidneys or kidney tubules, and the intestines. Both hyperkalemia and hypokalemia are going to have complications in both our cardiac and body muscle cells. So hypercalcemia, too much calcium, can lead to inhibition of neurons and muscle cells. And it can also lead to fatal arrhythmias. Hypocalcemia. If we don't have enough calcium, it's going to cause over excitability of cells by lowering the threshold that the cells need to reach to send an action potential. So you can actually end up experiencing muscle tetany or tetanus, and the muscles run out of energy and get cramped. Okay. So that's regulation of calcium. And again, that should be reviewed. Last thing is regulation of anions. So one thing to know, and I think your lecture notes already say this, is that all positive ions need to be balanced with a negative ion. And so what that means as far as our urinary system goes is you can see that here, that with aldosterone, whenever we reabsorb sodium, we actually also reabsorb chloride because we're bringing in a positive, and so we're actually balancing that by also bringing in a negative ion. And so you can see that here and here, that the reabsorption of sodium, chloride also follows. But that's not always going to be the case. Chloride is the most common to reabsorb with sodium. However, in acidosis, so if our pH in our blood is too low and we have too many hydrogen ions, then we may replace that chloride with a bicarbonate ion, which is also negative. So we're bringing in the sodium that's positive with a bicarbonate that is negative. We may replace that. Instead of bringing chloride in, we could bring a bicarbonate ion in instead to balance pH. And that's in the case with acidosis. And I think that's it for this part of fluid balance. So that's fluid balance 1. And if you have any questions, please reach out to me. Talk to you later.